Okay, cool. Sanjana, do you want to take it away?
Mhm. Hi, we're Team Gravity Wells, and we made a project called Song Belong. We built a music classification product which lets you know whether a song belongs to a playlist, to a given playlist or not.
So a little bit about our project. We decided to create a song classification system to tell whether a song belongs in a playlist, and we decided to do this using some machine learning algorithms. The machine learning algorithms that we tried to use were neural networks, SVM, and trees, and we tried to use these neural algorithms and networks to find out patterns in the data so that we could try to accurately predict whether a song belonged in a playlist or not, trying to find out all the patterns and predicting it. And we used Kaggle to collect the data sets. We used the pandas library to clean up the data sets and make them workable. Then we used various machine learning models to look for patterns in the data and to find correlations that would allow us to, of course, find the song that belongs in a playlist and which ones do and don't. And we used CodeCalc and GitHub to collaborate and run our code on. And we decided to do this project because music is such an important part of our lives, obviously, and it's very enjoyable and it might be very helpful.
All right, so we got all of our data sets from Kaggle. We initially had like a 12.8 million song data set, which is huge. We ended up merging it with another one, so we had like around 5.8 million songs, which is still pretty big. So we had a little bit of problems with like manipulating and cleaning our data, such as like the CoCalc servers crashing or like some column names not being uniform. But we got through it. And then below you can see we have a correlation matrix shown as a heat map. And what this is going to do is kind of show us like the intensity of the correlations between two values. So the brighter the color on the pixel, the more intense the relationship between the values are.
All right, so below this, we have what's called a pair plot or a scatter matrix, whatever you want to call it. It's basically just an in-depth heat map or correlation matrix that shows the correlations better. What you need to know about this is that the names with PL behind them are the average of the song attributes. So energy PL, for example, is just the average of all the energies put together, essentially. So looking at the pair plot, you can see that energy PL and loudness PL have a very tight correlation with each other. And same goes for energy and loudness, which would make sense because PL is the average of all the energy and loudness. So it would make sense that it's more tight. Otherwise, most of them don't really have any correlation with each other. They're kind of just noise, more or less.
So I made this scatter plot here and it shows the relationship between loudness, energy, and acousticness. And my motivation for creating this one is when I looked at the matrix that you saw earlier, I saw a very high correlation between the loudness and energy. So I decided to try putting that on a scatter plot, and I saw this, and then I actually tried adding acousticness to it, and I found out that although acousticness does not strongly correlate with energy or loudness, with both combined, it correlates with them very well. And you can also see that as a song has higher and higher energy, it becomes less and less acoustic. And I think the reason for this is because the more electric or high energy and loud a song is, less acoustic it's going to get, and yeah, the lower energy is going to lend to more acousticness as well.
Another scatter plot that we made was between time signature, energy, and loudness in terms of the playlist attributes. And so for this, we found that there was a pretty positive correlation between all three of the features. And so as like energy and time signature increases, so does loudness generally. And so from this, like we would like assume that maybe because energy, like higher energy songs are like generally associated with more loudness, and maybe time signature is associated with higher beats. And so maybe that is one reason for that trend. And then another one of our last scatter plots, another scatter plot we did was in terms of valence, danceability, and instrumentalness in regards to the playlist attributes once again. And so for this one, we found that valence and danceability have a positive correlation, but both have a negative correlation with instrumentalness. And so as generally as valence and danceability increases, instrumentalness actually decreases. And so one reason we thought for this is that potentially since danceability might be associated with more energy, loudness, or higher tempo, it might cause a decrease in instrumentalness as a result.
So I wanted to find out like the effects of some attributes on valence, which is like the overall positivity of a song. So I plotted this comparing loudness and valence and acousticness. You can see like the happier songs tend to have like medium to high volumes with pretty low acousticness levels, which kind of shows us that like slow and sad songs are normally the acoustic ones.
So we used a correlation matrix to see how danceability, tempo, and energy interact with each other. Though the clustering was not as strong, we can still see that the danceability was higher when the energy was high. You can also see that there were vertical lines formed by the data. This is visible when the tempo is at like 100, 125, and 150. This shows that a lot of songs actually use the same tempo.
So yeah, kind of branching out from the scatter plots, we also did some box plots to kind of like look at our data. So this one's in terms of time signature, energy, and key. And so one thing that we found throughout like our plots that use time signature is that there weren't any at time signature 2. And another thing we noticed within this graph specifically is that there's low variability among energy and key at time signatures 3 and 4, but there's higher variability at 0, 1, and 5 in terms of both range as well as the distribution of data points within. And so that was just something we kept in mind as we continued through our project. And then another thing we graphed was some violin plots. And so this one's in between time signature and loudness. And it's kind of just to look at more of the distribution of loudness in terms of time signature. And so for this, we found that generally as time signature increases, so the variability among loudness generally decreases. As you can see, like time signature 0 has the largest range, while time signature 5 has the lowest range. And another thing we looked at the distribution is that we found that it's fairly unimodal across all time signatures, and then also fairly right skewed. And then the last violin plot we did was in terms of time signature and danceability. So for this one, we saw that at time signature 2 and 0, there weren't that many points. But we found that the variability or the range is fairly equally distributed across the time signatures in the sense that most of them range from 0 to 1. But one difference we found from this in regards to the other violin plot is that some of the distributions were bimodal as opposed to unimodal, and then also more of the distributions were fairly symmetrical in this violin plot.
So for machine learning, we used support vector machine. So SVM is a supervised machine learning model. It is a classified method which groups data points into different categories using a hyperplane. Because SVMs classify data points based on their location, this machine learning method requires data with clustering to perform well. To train an SVM, we used SVC module from the sklearn library. However, we found this to be too slow and switched to a more optimized linear SVC model.
Another model we used is random forest, which uses decision trees. And decision trees they're like machine learning models that kind of use conditions to classify data. And so a random forest is like a bunch of these decision trees, and it bootstraps your data, which is like taking random samples from it, and it feeds your data through these decision trees, and it kind of tallies the results and gives you back the best one.
So when running the random forest model, we had to change some of the hyperparameters or arguments that were taken into account. The main ones we had to change were the number of decision trees and the maximum depth of each tree. And we found that in general, a higher number of trees gave us more accuracy, but made it slower. Now, our best accuracy was unfortunately only about 59%, but that was also the highest accuracy of any of the models that we used. And unfortunately, as well, this accuracy wasn't absolute, as decision trees are very sensitive to any change in data. So the accuracy measures would sometimes drop, although it wasn't only more than like 1% usually. So while this was less than ideal, it wasn't fatal.
So we were working on neural nets, and we set up a neural network. And basically what a neural network is it takes in a large amount of inputs. It runs it through multiple layers of neurons with varying activations and weights and biases. But what all of those are there to do is they're there to find patterns and correlations into data, and anything that can really allow you to strongly point to some kind of pattern unfolding, or some very complex pattern or simple pattern of this is how we figure out if a song belongs in a playlist or not. And our neural network did not perform very well. This might have been because we only had around, well, this might have been because we didn't have enough layers or neurons in each layer to find more complex patterns that were forming in this. The patterns might have just been too complex for us. So yeah, our accuracy rates were not that well. If we actually look at the results of the three different, right here is shown as the results of the three different machine learning models that we used in order to try and figure out if a song belongs. And as you can see, a random forest actually scored the highest here. Fortunately, our models were not able to achieve that high rate of success. The random forest model obviously being the highest rate of success. You can actually see more into the specifics of how good each model did here with a little matrix set up for one for each individual machine learning model.
So in just about 2.5 weeks, we were able to create this product that can attempt to predict whether a song belongs in a given playlist or not. We had a pretty limited team size and a bunch of technical drawbacks, but we still persevered and achieved an end result that we all liked. Despite the hours spent optimizing parameters, the accuracy didn't really reach where we wanted it to be due to the unpredictable nature of a lot of our models. But it can still be a stepping stone to greater things like true song recommendation or a genre classifier. And this project has definitely helped us gain some experience with like data science and machine learning.